In a constraint optimization problem, we have an objective function z that we want to optimize. In this case, z is a function of x and y. In order to optimize it, we need to take into consideration that it has restrictions. The restriction here is called g, and this is known as a constraint function. And it's called constraint because this function is equal to a constant. In other words, it has already a value. Graphically, as you can see, g is this green curve, and this means that z can be optimized either maximizing or minimizing the function, but the values that x and y can take to optimize z has to be in the curve of g. The direction of improvement depends on the goal. If we want to optimize z by maximizing, then this means that farther the origin, the better for the function. In contrast, when our goal is to minimize the function, we want the function to be as closer as possible to the origin. The optimization occurs when the objective function intersects the restriction at the point C. At that point, the slope of both the objective and the constraint are the same. Now notice something interesting. Here we have the gradient of the objective and the gradient of the restriction. If you see, they are actually very similar, and in fact, they are multiple of each other. However, for example, in the case of the minimization, and we know that this is a minimization problem because the gradient of the objective function is going towards the origin. So in this particular case, you can see that the gradient of f is a multiple of the gradient of the restriction times a scalar. In this case, this scalar is called Lagrange multiplier. And we add a negative sign just because, as you can see, one is going towards the origin and the other is going farther from the origin. Now, what we can do is do some algebraic operation and move this minus lambda times gradient of g to the other side. And this is the property that we will need for the Lagrange optimization. Notice that the gradient of the objective function plus the Lagrange multiplier times the gradient of the restriction will be equals to 0. Let's keep in mind the previous relationship because we will use it in this slide. So we were talking that in a constraint optimization, our goal is to optimize z subject to a constraint function. Here both z and the function g depend on x and y. Now let's define what is a Lagrange function. The Lagrange function is represented by L equals, first we will write the objective function. So here we have x comma y. So this is our objective. But now we will subtract this function. But in order to subtract it, what we will do is a trick. Notice that g is equals to k. So this means that if we rearrange, we can move g to the other side. And as you can see here, k minus g will be equals to 0. So let's write that in this parenthesis. K minus g. And remember, our goal is to find a parallel between these two that actually optimize the function. And as before, let's multiply by a lambda. Now the question is, if we are trying to optimize this function, why we are going to optimize the Lagrange instead? Well, if you notice, the only thing that the Lagrange did was to combine both functions together. But if you see here, k minus g is 0. The only thing that I did, in other words, was simply to add a 0, because 0 times lambda is 0. In other words, in the Lagrange, we are actually adding or subtracting a 0. Therefore, for example, if we maximize the Lagrange, is the same as just maximizing the function that we wanted to optimize. Notice that the Lagrange has three variables, x, y, and also the value of lambda. This is because, if you remember, and you will notice that in a second, our goal will be to find the point in which both intersect, and this depends on the scalar. However, there is something interesting in the Lagrange function. Even though the lambda is an important multiplier, normally we will not find the value because normally we will be able to simplify it. But let's continue. So here we have the Lagrange function. Remember, it's equals to the objective function, the original objective function, minus, and we put a Lagrange multiplier, times the restriction. But remember, we put always the constant minus the function. And because this is equals to this means that we are multiplying the lambda by a 0. And in other words, the Lagrange and the objective function are the same. Now the next part is simply because we have three variables, x, y, and lambda, we take the first order conditions. With respect to x, this is a partial with respect to x minus lambda times. Notice that here we will have the derivative of k with respect to x is 0 because k is a constant. And here we have the partial derivative of g with respect to x. And this must be equals to 0. Let's continue with the derivative of the Lagrange with respect to y. Here we have that is going to be the partial derivative of f with respect to y minus lambda times, again, derivative of k with respect to y is 0, and then minus the partial derivative of g with respect to y. And this we set equals to 0. And finally, we will have the Lagrange with respect to lambda. The derivative of the function with respect to lambda is 0 because the objective function doesn't have lambda in it. So this is a constant. Minus derivative of lambda with respect to lambda is simply 1 times k minus g, which is a function of x and y. And we set this equals to 0. Now from here, we're going to have 3 equations. And pay attention to this. Here we have the partial derivative of the function with respect to x is equals to negative times negative was positive, and we are moving lambda gx to the other side. So this is minus lambda gx. In a similar way, here we leave the partial derivative of the objective function with respect to y in one side equals, then minus times minus is plus, but because we are moving it to the right hand side, it becomes minus lambda gy. And finally here, notice that is minus 1 times k minus g. 0 disappears. Then we divide everything by minus 1, and then we get k minus g equals 0. And continuing with this, you will notice that we will obtain the original function, the original restriction. Notice that when this is an equation, the restriction is an equation, this always happens. So here we have the 3 equations. Then from these 2, if we divide them, notice what happens. The ratio between the partial derivatives will be equals to the ratio of the partial derivatives with respect to the restriction. So this is very important because with that relationship, we will get the relationship between x and y that later on we will need to insert in the third equation. And now, why it was important to know the gradients? Because if you see here in the gradient, we had this relationship already. We said in the gradients that the gradient of the objective function was the negative lambda times the gradient of g. And remember, the gradient was simply for f of x and f of y. So these two came from here. And as you can see, we use actually the reversal to prove it. So this is in gradient terms. So this is the logic of the Lagrange function, which is represented in summary here. Now notice that in some points you will need to use the Kramer's rule when it's possible. And we will see that in the following examples.